well, two things that are on Canvas, right? So the Xor thing um, is, I made a minor modification of this earlier this morning to correct a slight mistake, but um, it should have been pretty obvious. So here's the schematic for an Xor gate. Essentially, you build three separate individual gates and then put them together or connect them together. The NAND gate, you've already built that, right? So one of your breadboards has a NAND gate. Well, you should have already built that. Okay, gonna stare at you guys. Yeah. Okay, so great. And then the two other things you need to build are, so the little dashed lines, basically each one of those should be one breadboard worth of stuff. Okay. You don't have to put them all on separate breadboards, but it'll be easier to do it that way because then you can concentrate on doing one piece at a time, make sure they individually work, and then put them together. Okay. Good, Xander? Okay. We're good. Okay. 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 So let's talk about the how I know that this whole contraption actually will be an XOR gate. Okay. In order to demonstrate that, let me go back to the iPad. Oh, damn it, iPad. Okay, here we go. So, what does XOR mean? Exclusive OR means one or the other, but not both, right? So if I asked you, right, do you want pecan pie or do you want apple pie for dessert? What's the intent there? Yeah, that you can have one or the other, but you can't have both. And it's also reasonable, like you could choose to have neither, right? But you having both is verboten. Okay, so A or B, this is true, means that you actually are having pie, one of the two pies. Okay, and not and means you're not having both of them. Okay, and both of those things need to be true, which is why they go into an AND gate. Okay, so high level wise, what we're making is the thing in the box there. Okay, an OR gate, a NAND gate, and an AND gate, and putting them together in that order. Okay, so individually wire up each one and make sure they work, but then the ultimate contraption will be we take the output from the NAND gate and the OR gate and use those as the input for the AND gate. And then the output from it is the ultimate output of XOR. Okay. Now, XOR has a schematic symbol, which is this here, and that's essentially what we're building, right? We're building it out of three other gates, or really a few more than that. Okay, now somebody this morning asked, what's the difference between NAND and XOR? And the difference is, here's the truth table for NAND, there's the truth table for XOR. They're off in one position from each other. Okay, so they don't have the same truth table, so that means that they're genuinely different Boolean operations. Okay, and great. Okay, so is that okay? Yeah. All right, now let's go back to the schematic in terms of how we'll actually wire this stuff up. Okay, so let's look at the NAND gate. So first off, over here on the left, I've got these two things that are running vertically. What are these? What's this stuff? Yeah, those are the LEDs for the inputs, just so you can see what the input actually is. Okay. This symbol here is the schematic or the symbol for an LED. And what's that? The resistor. And what resistance is it? They're all 330s because we're operating at 5 volts. Okay, so you've got your two lights to show you what's going on. All right, then for the NAND gate, well, how many transistors did it take to build that? 4, right? 2 of which are PMOSs, and the complementary pair, which are NMOSs, okay? And notice that for the NAND gate, the NMOSs are in series or parallel. They're in series, and therefore their complementary PMOSs are in parallel, right? So it's always complementary like that. Okay, and then this LED over here would be the output that we just looked at to see if we were getting the correct thing. Okay, now when you guys built this, the NAND gate already, I've shown here that there's a split and the output keeps going and there's also the light. You would not have had this second wire because you didn't need it if all you were building was the NAND gate. You only will need that when you put this together with other gates or other things, okay? All right, so let's contrast how are we going to build an AND gate if we've already know how to build a NAND gate, okay? And the way that you do this, which may seem a little bit backwards, is we build an AND gate by building a NAND gate and then negating the answer, okay? So this first part of the AND gate, what is this right here? That's an AND gate. And then what's this little bit at the end? An inverter, okay? So we build the NAND gate and then tack an inverter on to make it an AND gate, okay? And then like before, we've got our LEDs, input and output, okay? When you first build the AND gate to test it, where you've got NAND output and OR output, actually make those input A and input B from the Arduino, okay, to initially test it. And then when you put all three of the boards together, you'll actually, the inputs for the AND gate will be the outputs from the other two gates. Does that make sense? Okay. All right, now contrast that with the other, the OR gate. So how do I build that? Well, I do the same trick I did with the NAND and AND. I first build a NOR gate, and then I negate it. Okay, which again seems maybe bass-ackwards, but them's the gates. You see what I did there, right? Yeah. Okay, so this part right here in the middle is my NOR gate. Now compare that structure to the structure of the NAND gate. What's different and what's similar? Well, I still have 4 transistors, right? 2 NMOS, 2 PMOS. For the NAND gate, how were the NMOSs? They were in series. How are the NMOSs here? They're in parallel, right? And in the NAND gate, the PMOSs were in parallel, but how are they here? In series, right? So they're flippied in some sense. Okay, so this, you guys buy, is a NOR gate. And then I use the output of it as the input to an inverter, and that turns it into an OR gate. Does that make sense? This is not the only way to make an OR gate, but this is how you do it in the CMOS style, okay? And the reason I'm kind of hammering it the way the CMOS style is because that's how processors are actually manufactured using this sort of arrangement. So I might as well look at what we actually use, even if there's other ways to do it. Okay. Now, if you just Googled CMOS Xor Gate, you can find there are other schematics for how to do this, okay, that are actually a lot simpler than what we have. Okay, so why would I want you guys to do it this slightly more complicated way? Yeah, bingo. This way you guys know how to do each individual constituent gate. You know how to do a NAND, you know how to do a NOR, you know how to do an inverter, you know how to put those together, and you know how to then put all 3 pieces together. Okay, so that was a deliberate choice on my part. The other reason is that each individual thing in the dotted line, so each individual breadboard, you can concentrate on that piece, get them all working, and then the second step would be to put all 3 of them together, right? Yeah, okay. The other reason is to explain why some of the other schematics that you can find are equivalent to this would require us to go through a significant amount of Boolean algebra. Okay, so in the same way that like in math class, could you take some really horrible algebraic expression and simplify it and collect like terms and maybe factor in clever ways and do all kinds of stuff to write an equivalent but different looking expression? Yes. Same thing with Boolean algebra, right? I could take the A or B and not A and not B, right? So the Boolean expression that we've essentially made with this circuit, and by applying the rules of Boolean algebra and kind of simplifying it, I can come up with different looking but equivalent Boolean expressions that might require fewer transistors to wire up. Yeah. Okay. So it may seem like I've made it more complicated than it needs to be, but yeah. Okay. Yes. Okay. So there's that. When you do them all separate, you may, and I've got some extra LEDs. So actually, I'll just put like a big baggie of the LEDs with the cart of buckets. And if you need to grab some extras, then just grab some extras. That's pretty easy. Yeah, because I think there's not enough. Because I think you only have 5, and I think I've used 9 in the diagram. Okay, so I'll add. I'll put the bucket of the extra LEDs and just grab it as you wish. Okay. Um, okay. So the second question, though, related to that is, notice that how many plus 5 volts have I drawn on here? There's a bunch of them, right? But how many plus 5 volt pins do you have on your Arduino? You only have one. Okay. So how do you use one pin off the Arduino to drive all of this stuff? Well, if you go into a breadboard, then you can take another wire from the breadboard to someplace else. Okay. So you have to kind of chain the breadboards together to have power to all of them. And same thing with pin 2 and pin 4, right? You'll have to go from the Arduino to a breadboard spot and then from the breadboard over to a different breadboard spot, because there's only so many pins available on the board. Yeah. Yes. Okay. Yeah. If we were putting together like 20 breadboards or something, then yeah, we might start to run into issues. But for 3 of them, it's not. At the amount of current and the voltages and stuff we're dealing with, it's not going to be a problem. Okay. Yeah. If we built like a breadboard the size of the room or something, then yeah, we might run into problems. But it won't be an issue for this. Okay. Okay. So does that make sense? Yeah. Okay. So when do I want this done? Thursday night. Okay, which is to say before class Friday, because in class on Friday, what are we doing? The video people are coming at 11:30. Okay, so before that, we're going to do our discussion, and then we'll have the breadboards because that'll be very photogenic. Okay, for the video people, right? So if you could wear, you don't have to wear shirts and ties and stuff, but don't look like complete slobs on Friday. That'd be great. Okay. Yeah. Yeah. So, yeah, so don't look like complete slobs. Okay, now I know I'm dumping a lot on you guys all at once, especially given that it's homecoming, but to address one of the questions that seems to have been raised on Yik Yak, actually all of us professors, we get together every week and decide how we can all throw as much stuff at you all at once and make all of our papers and exams all be on exactly the same day and like laugh maniacally while we're doing it in a smoke filled room where we're drinking whiskey and smoking cigars. Yeah, like we totally plan this to maximize your suffering. I mean character building. It's character building. Okay. Okay. The other thing that we're going to do Friday, right, are the discussions. Oops, that is not the. Okay, that was about to be a FERPA violation. Okay. Okay. So the other assignment, the other thing that we're going to do Friday, right, is our discussion. Where the heck is it? Yeah, here it is. Okay. So I've posted here 3 PDFs. They're not real technical reads. They're all from like news sites and that sort of thing. Um, about 3 different examples of overflow error catastrophes. And so we'll kind of talk about the readings both in small groups and collectively, and then also kind of maybe dive a little bit more into the technical aspect of exactly what was different about each overflow error situation. Um, and the first one, the Patriot Scud, that was from the first Gulf War. People actually died from that one. The Boeing 787, nobody's died. And the Ariane 5, it blew up and cost millions of dollars, but nobody died or was injured, right? So, um, yeah, and they're all related in terms of what errors they were, but not identical as to how they manifested, which is kind of interesting. So, um, anyway, so we'll talk about that. Okay, good. So the next thing I wanted to do is let's talk about. We've spent a fair amount of time talking about how numerical data is stored in a computer, okay? In either as integers in two's complement or as floating point numbers. And we did the 8-bit stuff just for simplicity, really. But, you know, we could do it for 64 bits if we wanted. Okay. But point being, we were looking at how numbers got stored. And there were 2 different systems, the integer set of system and the floating point stuff. Okay. But clearly, we'd like to be able to store other types of data on a computer, like text, uh, or sound or graphics or right movies or whatever, right? So there's lots of other types of data we want to be able to store, and we need to look at how do each of those um, or how do these sort of primitive pieces of data get stored. So we'll also look at text. All right, so what I have here is a simple little text editor. It's a console text editor called Nano, um, and I've typed in a relatively simple thing. Um, and okay, especially Phi Delta and Fiji. Apparently, it's getting a little rough. If for once we're not talking about you poor betas and your hats. Uh, so yeah. So how is this data actually stored? Right. So I just typed all this stuff out, but it's got to be stored in as a bunch of ones and zeros, right? So there needs to be a scheme for how to organize that, and that scheme, or one of the schemes, is called ASCII. All right, how many of you guys have seen The Martian? Yeah, the movie. All right, so what's one of the, do you remember the part in the movie where he's like, surely somebody brought an ASCII table with them, and one of the other astronauts did? Okay, so how did he use this ASCII table? Well, in the movie, right, he went out and drove and found the old rover that had the rotating camera on it. And he brought it back and he hooked it all up. And then he put stakes around it with letters on them. What letters did how did he arrange that stuff around? Do you remember? I feel like I just need to pull up that scene from the movie. I really should just let me just do that. Okay. Um, all right, so let me go back over to the Mac. Oops, I want Mac, Auto, and I need a web browser. Okay. Okay, hold on. Let me get the audio so that you guys can actually hear this. Okay, so I need my output to be Blackmagic device HDMI, and then I need the Mac to be on for audio, And then I need to turn the audio on over here. Guest input is the source. Okay, let's hope this works so you guys can actually hear it. Is it coming out of the... It's coming out of my TV. Can you guys hear it? Okay.
Incoming. Are you receiving me?
Let me turn it up a little bit.
No. Okay. Point the camera at yes.
32-minute round-trip communications time. All he can do is ask yes/no questions, and all we can do is point the camera. This won't exactly be an Algonquin roundtable of snappy repartee.
Tell. Just point the camera.
Roger that. Pointing the camera.
Yes! Yes! So here's the rub. Somehow, we have to have complex astrophysical engineering conversations using nothing but a still frame camera from 1996. Luckily, the camera does spin, so I can make an alphabet. It can't be our alphabet. 26 characters plus a question card into 360 gives us 13 degrees of arc. That's way too narrow. I'd never know what the camera was pointing at. Ooh. Hexadecimals. Hexadecimals to the rescue. I figured one of you guys kept an ASCII table lying around. I was right. Ladies and gentlemen, I give you super nerd Beth Johansson, who also had copies of Xor 2 and Leather Goddesses of Phobos on her personal laptop. Seriously, Johansson, it's like the Smithsonian's loneliness on there. Not that I'm complaining. Yes. Who am I to talk about loneliness?
All right, so what's he doing? He realizes that 26 letters of the alphabet plus 10 digits plus punctuation is just too many things to go around the circle. So he figures, okay, I'll only put 16 things around the circle, 0 through F, hexadecimal, right? And then right, so then they add the pointer to make it easy. Okay, and now he's going to wait and sit there and transcribe it and fall asleep. And then look at the ASCII table. Okay, let me pause it right there. Okay, so let's go back and actually look at what he's writing on his pad. If I can get it there. Okay, 4847 or 48 4F 57. Okay, and he's looking at a table to record off what characters are referenced there. Okay, so let's look at an ASCII table. This is essentially what he's doing, right? He's looking at this and saying, okay, what was the first one? What did I say? 4, 8? Okay, 4, 8 is, so the column that we want to look at here is the third column because those are the numbers written in hexadecimal. Okay, 48 capital H. Okay, what was the next one? 4F, which is capital O. Then what was it? 58, 57, W. Okay, so what was their first message? Let's keep watching. How? And they didn't put spaces in there because they figured, you know English, he knows English, he can, how alive, right? And then he didn't really need to rewrite that. That's just for the sake of the movie, right? But they're basically asking, how the heck are you alive still, right? And so then he's going to, right, I'm okay, impaled by antenna, biomonitor destroyed, right? And he can write, and they can, of course, see the picture.
Now that we can have more complicated conversations, the smart people at NASA have sent me instructions on how to hack the rover so that it can talk to Pathfinder. If I hack a tiny bit of code, just 20 instructions in the rover's operating system, NASA can link the rover to Pathfinder's broadcasting frequency.
So then he doesn't have to do all of this manually, is the plot there. Okay, but let's look at the table here and see. Okay, so ASCII was originally a 7-bit scheme, okay, which allows you to encode 128 different things. Okay, now 128 is a lot if you think about the order of the English alphabet, right, or Latin alphabet, because how many letters do we have? 26. Okay, maybe we actually should say 52 because we have lower and uppercase. We've got 10 digits. We've got all the different punctuation symbols, space, less than, greater than, all the kind of special characters that we use for things, a dollar sign, right? But we're still, 128 is still plenty of them, okay? And, but there are some weird things in ASCII that aren't going to make sense initially. Okay, there are printable characters, which are characters starting at 32, that's decimal, which is 20 hex, up through 127. Okay, all of those are things that you can actually print on a paper. But there are 32 characters that aren't actually printable characters. Okay, and to kind of explain why some of these things need to exist, we kind of need to go back in history a little bit more. How many of you guys have ever used a typewriter? Okay, did you ever use it for anything other than just playing with it when you were a kid, or have you actually typed something on a typewriter? Really? Ah, apparently this is what they do to character builder over at at Delt, right? You type out old Wabash on a typewriter. Of course, right? And I'm sure no ethanol containing substances were involved in the decision or act of doing this, right? All right, so you type on a typewriter. How does it work? You hit a key and what happens? There's a little arm, and at the end of the arm, there's the character, right, in metal, and it hits a little pad of ink, and that strikes the paper and leaves a little bit of ink, right? And then it spring loads and it falls back down. And then you hit another key, and another arm comes up and smacks. And every time you hit a key, what happens to the carriage? It shifts over one spot, okay? And after you type a full line worth of stuff, what happens? It reaches the end, and how do you know it's reached the end? Because there's a little bell that goes ding, and then you advance the line feed by one and push the carriage back to the left, and then the poll process starts again. Well, guess what? The characters 0A, 07, and 0D are for. Yeah, these are all old typewriter ideas. Carriage return, bell, line feed, and stuff. Okay. And this stuff is there because back in the day, how did you get output from a computer if you didn't have a monitor or a screen? You hooked it up to a teletype machine. Okay. And a teletype machine is essentially a computer controlled typewriter, right? So instead of having buttons, it's all electrically triggered. Okay, but like literally, it's like a typewriter being controlled by a computer. And so you need to be able to send commands to line feed or detect whether or not a bell has just rung or whatever, and those things are still part of ASCII. Okay, but importantly, either the line feed or the carriage return, or perhaps even both, tells me that I've reached the end of a line of text. So when you're typing something, you're typing a paper and you hit enter, well, that needs to be encoded so that when you reopen the paper, Word or whatever has the line separated, right? If you want to break the line early, you can do that, and that has to be encoded. Okay, so let me go back to the Pi, and let's look at this simple little text document that I typed out, okay? Wabash always fights, especially Phi Delta and Fiji, okay? So 5-7, what is that? That was the capital W. 6-1 is lowercase a. 6-2 is lowercase b, and so on, okay? And then over here on the right, it's displayed, because I told it to, it's displayed the characters in the same order. So 5-7 is W, 6-1 is lowercase a, 6-2 is lowercase b, 6-1 is the second a, and so on, okay? And then there's a few other things. So for example, 2-0, what does that correspond with? It's the space, okay, which is not technically printable, like, because it's the absence of printing something, but it's still a character. And if I didn't have that, there wouldn't be a space there, okay? Furthermore, the way it's arranged this is it's showing me how many bytes are here. This is 16 bytes at a time, okay? That's just the way it's formatted. It makes it a little easier to read. So 16 bytes at a time, and what about the, I hit enter after Wabash always fights, okay? How is it displayed it over here? It's displayed it as a period, but it's not really a period, okay? What is the character that we see right here? 0A. What was that one from when we were looking at the chart? It was the line feed, okay? And that meant go to a new line. Now, this is something that's very annoying. Back in the day, computer companies and different systems didn't all use exactly the same scheme for ending a line. On Windows, it's 0A followed by a carriage return, 0A, 0D. On Unix-based system, which means Mac, basically since the year 2000. So Apple since the year 2000, any Linux machine, Chrome, Chromebooks or whatever, because those are all Linux-based, only put a line feed to terminate a line. Windows does line feed followed by carriage return. Other systems, like my Commodore, uses only the carriage return, not a line feed. Okay, so the standard, there was no, and there still isn't, standardization as to how lines are supposed to be terminated. Okay, yeah, and then the rest of the characters are, well, the rest of the characters. Okay, make sense? All right, so let's go back to that ASCII table, though. It's a perfectly good table, you know, loads of fun. Okay, let's look at all the symbols that we've got. It's a pretty good list of symbols. Anybody have any problems with this list of symbols, though? Anything missing? Special characters? Okay, and also, what about if you want to type languages other than English? Well, this is the American Standard Code for Information Interchange. That's what ASCII stands for. So because of that, MERCA, it only has the English alphabet and stuff in it. Okay, but what about if you want to type something like Spanish or French or you know, other Romance languages that use a Latin alphabet but that do have special characters, like in Spanish, right, there's the N with the little tilde above it, or you have some of the vowels that have acute or grave accents on them, or in French, there's the C with the little dangly bit. Well, are they here in ASCII? Nope. Okay. And thus was birthed the extended ASCII codes, which adds another 128 of them and gets us some of the other symbols. So let me kind of zoom in on this. For example, the symbol for the euro, the symbol for the different letters that have accent marks on them that you might need in basically any of the other European languages. F, this is an old letter, so there's some obsolete letters in here that aren't used anymore. The thorn, that used to be part of English. We've got at least some of the Greek characters, okay, some other lowercase versions of things we've mentioned, okay, and so on. And some mathematical symbols, a few other things like that. Anything missing? Well, there's a fair bit missing, right? What happens if you don't use the Roman alphabet for your language? Right? Or what happens if you don't even use an alphabet at all for your language? Okay, so what languages don't have alphabets, for example? Okay, Chinese, Mandarin Chinese, or basically any of the Asian languages. That's not technically correct. So Korean, for example, it's not really an alphabet. It's called a syllabary, and there's a slight distinction between those two things. But Chinese, Mandarin Chinese, right? How many different symbols are there in that language? It's like thousands upon thousands of them, right? Because it's pictogram based rather than being alphabetic based. Okay, fine. But how am I going to encode all of that if I need thousands upon thousands of different symbols? Okay, so what's extended ASCII called? It's called Unicode. All right, so let's look at Unicode. Okay, so Unicode says you can use up to 32 bits to encode characters. And that allows you to encode basically like 4 billion different things. And I think we could agree that that's a whole lot. Okay, now, Unicode has in it everything that's ASCII is in fact valid Unicode, which is nice, which it means it's backwards compatible. Okay, but there's a crap ton of other stuff in Unicode, including all of the emoji. Okay, so was anybody on Yik Yak earlier and noticed that there were like 12 cheeseburger emojis in a row? That was the first class because we were talking about the cheeseburger emoji. Okay, and so in particular, like let's look at the emoji. And they do actually have some interesting stuff as to what are the most commonly used emoji, right? Okay, but yeah, okay, so all of these different symbols, right, are, well, or here, let's do the cheeseburger emoji. All right, full emoji list. This is probably a very big document. Okay, so here's all the different emoji, right? All the different silly smiley faces and frowny faces and the various piles of poop. And so where's the burger? Is it not on here? Or is my computer just being really slow? Oh, it's not found. Okay. Yeah, I guess I don't see it on here, but okay, fine. What about the gun? No, doesn't have that, or at least not on this list. But okay, let's go back up to, we'll just use the poop emoji as an example, okay? So, the poop emoji, all right, its Unicode code is 1F4A9. Okay, so that number has been assigned to be the number that will represent the poop emoji. Now, what's with all the different poop emojis? Huh? Yeah, it's a lot of different versions of the poop emoji, okay, and these are sorted basically based on which system or which program is going to be displaying it, right? So the poop emoji on an Apple device looks like this. But if you've got, does anybody have an Android phone? Yeah, your poop emoji looks like that. Okay, and if you put it on Twitter, it looks like this, right? And if Gmail, it's got like the flies around it because it's a stinky pile of poo. Okay, so those are all the same Unicode number, but how the character is displayed differs based on what system you're on. Okay, and so the clown emoji, or I mean, they all look different, right? But the poop emoji on Apple looks slightly different than it does in Google. Actually, you know what's kind of freaky about the Apple one? You know the ice cream cone emoji? It's an ice cream cone with a poop emoji that's made in white on top without the smiley face and the eyes. You'll never look at an ice cream cone again the same way. Okay, right. So how these things are displayed is not the same as how they're encoded, right? The encoding for all of them, Google, whoever, is 1F4A9. What's different is each system has graphics stored someplace, and when it sees, oh, Unicode 1F4A9, poop emoji picture, .gif goes there, okay? And so on, okay? And this occasionally gets people really irritated. I was talking about the cheeseburger emoji because, so get out your phones or your computers or whatever and type you can do it in Yik Yak or whatever, the cheeseburger emoji. Okay, and then I want you to describe how the cheeseburger emoji looks. And while you're doing that, I'm going to see if I can find it on this list because it is a lot of emojis. Did I pass it? Hamburger. Here we go. Okay. All right, so what is it? 1F355. Oops, that's not what I wanted. Well, okay. So how does it look on your, who has an iPhone or Apple device? Okay, describe the cheeseburger. What's at the bottom of the cheeseburger? There's a bottom bun, followed by lettuce. Okay, I don't know what monster puts the lettuce right after the bun. Okay, but this is just intolerable. Followed by the burger patty, followed by the slice of cheese, followed by the tomato, followed by the top bun. For a while, they actually had the cheese underneath the patty. That's not okay. Okay. So yeah, they do change how these things are displayed. Yeah. So I do bun, patty, cheese, then lettuce, then tomato. And if I've got pickles, those go on before the lettuce. Okay. And then on top of the tomato, then this is where the ketchup and mustard go. Okay. And if anybody has a problem with that, the door is right over there. Okay. Of the lettuce? Yeah. Okay. Well, so the point, though, that I want to make okay, as we finish, is the way it looks on the screen is not the same as it's encoding, okay? And the way it can look actually can change. So those of you with Apple devices, it's been a while, but the gun emoji is what on an Apple device? It's like a little squirt gun. Well, it didn't used to be that, right? They changed it, but it's the same Unicode character. Okay, and then if you guys will humor me, the last gripe that I'm going to have, of course, is the fact that we have all these stupid emoji, but in the 90s, when somebody proposed to the Unicode people to, well, when the Klingon Language Institute proposed to add the Klingon alphabet into Unicode, you know what they said? No. But now we have all these stupid emoji. And that grinds my gears. So, all right. See you guys on Friday.